Hi everyone. So in the last video we have discussed about Heisenberg uncertainty principle and we have discussed the non-existence of electron inside the nucleus, the application of Heisenberg uncertainty principle. Today we are going to deal with the wave function. As we are talking about matter waves, the matter waves, they are always characterized by a function which is going to be a variable of the space and the time. And this wave function, it determines the physical situation in the case of quantum mechanics. And this is denoted by the function psi, the function that is denoted by psi, that is the wave function, which is a function of the position, that is xyz, that is the position of the particle, or we can say it as space, and the time coordinate. And the psi of r comma t, this is given by a into exponential of I into kx minus omega t, where a represents the amplitude of that matter wave and the exponential part is going to represent the phase of that matter wave. And k, that is the propagation constant, omega, that is the angular frequency, and t is the time that elapsed. And this wave function is not having any physical significance. To obtain the physical significance, we are going into a term called probability density function. In the case of classical mechanics, the square of magnitude of that electromagnetic wave will give you the energy density, or we can say it gives the radiation density. The same way, here in quantum mechanics, we can explain the wave function that is associated with any particle. Here, as we are taking psi as the wave function that is associated with the particle, the square of absolute value of that wave function is going to give you the probability density of the particle. This probability density, it is nothing but the probability of finding the particle in a particular volume. So that is given by psi star, where psi star, that is the complex conjugate of that wave function. So the square of absolute value of the wave function is going to give you the probability of finding the particle. So this is having the physical significance. So the product of psi and psi star is going to give you a real and positive value. We have taken psi as a complex number. So if you multiply with a complex conjugate, we are going to get a positive, real and positive value. So that real and positive value is the probability density, that is the probability of finding the particle. Next, about the properties of that wave function, we are going to derive a wave equation, and from that wave equation, by applying the boundary conditions and initial conditions, boundary conditions, we are going to obtain the solution. So that solution, it is going to give you a number of solution. So to find out the correct solution, that wave function obtain, what we are going to obtain as a wave function, it should have the following properties. First one, the wave function, it must be finite in nature, and next one is it must be single valued. The wave function and its first derivative, it must be continuous in nature, and the fourth important one is the wave function must be normalizable. So if the wave function satisfies all these properties, then we can say that as the eigen wave function.